Thank you very much for listening to my talk. I'm going to present results from a new cosmological analysis of the eBOSS Lyman-α Forest that we're just completing here at UC Riverside. So before I begin, I'd like to thank the students who were involved in this work. So my recently graduated student, Dr. Martin Fernandez, and also Ming-Feng Ho and Mati Keslu, who are on the job market in the fall. I'd like to also highlight the archive number of the paper, first paper connected with this. So what is the Lyman-α Forest? So the Lyman-α Forest is the absorption from the overlapping redshifted Lyman-α lines from neutral hydrogen in the intergalactic medium along the line of sight to a quasar at redshift 2 to 5. So because the gas density traces the dark matter density, because large halos tend to have more gas density in them, this is a tracer of structure formation at redshift 2 to 5, and we can use this to measure the growth of structure at these redshifts. So the specific summary statistic that we are measuring is the 1D flux power spectrum along the line of sight to the quasar in eBOSS SDSS DR14. This is a velocity spectrum quantity, which has velocity units. It goes from K of about 10 to the minus 3 seconds per kilometer to K of 2 times 10 to the minus 2 seconds per kilometer. And I put the conversion factors here between velocity units and physical megaparsec and co-moving megaparsec units at redshift 3. And you can see the largest scales we're measuring about K of 0.1 h per megaparsec, and the smallest ones are about K of 2 h per megaparsec. So these are quite small scales by cosmological standards. They are scales in which the structure is nonlinear, and that means that we need cosmological simulations. So we need them not just to model the growth of structure on small scales, but also to model the pressure in the gas. So because the thing we're observing is gas, and gas is not a perfect trace of the dark matter, we do need hydrodynamic simulations. So I have performed a large suite of these simulations, shown this wonderful movie here, as the sight line runs through the simulation box. This is the Priya Cosmology suite, named after my wife Priya, and they all take place in a 120 megaparsec box. I have 3 high-fidelity simulations, each with 3072 cube particles. This gives them a resolution about 10% better than the illustrious TNG simulations. I also have 48 low-fidelity simulations with 1536 cube particles, and these are really there, although the resolutions are lower, there are enough of them they can really explore a fairly large cosmological parameter space. So I don't like to brag, but these are quite large simulations, right? These are quite high resolution, they're quite high particle load, and they're pretty nice. Also, uniquely for cosmological simulations of this type, these are full hydrodynamic simulations. So these have a full-on galaxy formation physics model with star formation, stellar feedback, black hole feedback. And the model used is that for the asteroid simulation, which was a very large-scale simulation. So why do we need all these simulations? So we need all these simulations to do cosmological inference. So the goal here is that we want to take a prediction for the flux power spectrum for an arbitrary set of cosmologies and compare it to the observed flux power spectrum from eBOSS. So to do this, we ideally need an interpolation routine, something which can use a Gaussian process or something similar to predict the flux power spectrum even for cosmological parameters we didn't actually run. I'd like to use an analogy here. Here on the right, we have an early map of the world. And in this map of the world, the person who made the map knew someone who had been to Massachusetts, knew someone who had been to South America, didn't really know anyone who had been to the center in here, hadn't really been to Central America. So the person just kind of guessed and said, okay, well, maybe these lines kind of join up in the right kind of way. Let's just draw a line between them and guess where the coastline is. And that's kind of the thing that we're trying to do, right? We have a simulation here at the cosmological parameters that correspond to Massachusetts. We have a simulation of the cosmological parameters that correspond to South America, and we're trying to guess what the coastline in between looks like, or what the flux power spectrum in between looks like. The traditional way to do this is to run a large number, around 50 or so simulations, all of the same resolution, and to use a Gaussian process to interpolate between them. It's quite difficult to run 50 large cosmological simulations with the particle number that we require here to resolve the Lyman-α Forest, which is the high-fidelity node of our simulation suite. So to get around this, we've come up with this new technique called multi-fidelity emulation, which is really the brainchild of my student Ming-Feng Ho, pictured here working on a telescope. And the idea here is that we combine simulations at different resolutions to try and produce an interpolating function that can produce results for the flux power spectrum for arbitrary cosmologies as if we had run a high-resolution simulation at that set of cosmological parameters. So how does this work? So essentially what we're doing here is we run a lot of low fidelity simulations and then we correct them with a few high fidelity simulations. So the low fidelity simulations are supposed to explore cosmological parameter space, and the high fidelity simulations, there are just a few of them, and they build a correction function. And this correction function can importantly be cosmology dependent. So here on the right, I've shown you some representative flux power spectra at a series of redshifts between redshift 5 and redshift 2.2. And you can see that each of these blue lines is the ratio between a high fidelity flux power spectrum and a low fidelity flux power spectrum. You can see that they are a bit different, and that's because the correction function is a little bit cosmology dependent. Also, you can see that they don't go straight through one, right? So the cosmology correction function is actually doing something. So multi-fidelity emulation is really absolutely integral to making this program work. This red line is the ratio of the high fidelity simulations to an even higher fidelity simulation in a much smaller box, which is supposed to demonstrate that high fidelity simulations are actually converged. They're as high resolution as we need them to be. So again, the trick here is that by using multi-fidelity emulation, we're able to get by with only 3 high-fidelity simulations, whereas most of the actual cosmological power is coming from the 48 low-fidelity simulations, which cost a factor of 10 less than the high-fidelity ones. So we're able to run a lot more simulations than we otherwise would be able to. So what happens when we do this? So we put all this into our interpolation routine, we build the Gaussian process simulator, and we want to test whether it works. The way we do this is called leave one out validation. So what we do is we build emulators leaving out one single simulation in turn, and then we take the average prediction error for each of these simulations and we sum it up. And this is the plot that we get. And you can see that on average, the emulation is about 1% accurate. So this is this gold graph is the high fidelity simulations. This gold graph shows the accuracy of predicting a high fidelity simulation from the multi-fidelity emulator. And I want to make clear that we only have 3 high fidelity simulations, right? So when this prediction is going on, it's an emulator built with only 2 high fidelity simulations. It's missing 1/3 of the information they would otherwise have. So this is a very conservative estimate of the accuracy of our interpolator, and it's already about 1%. So this is actually, I think, accurate enough. The real emulator is going to be a little bit more accurate than this because it has 30% more information. Single fidelity predicting the low fidelity simulation, which is not quite converged, but you can get an idea as to what the cosmological parameter exploration is doing. This is accurate of about 0.2%. So this is really a pretty accurate emulator. So what are the parameters that we're using in my emulator? So the parameters we're going to use are, first we need 2 cosmology parameters. We need an amplitude and a slope of the matter power spectrum. These amplitude and slope are measured at 0.78 h per megaparsec. This is the same scale invariant, almost scale invariant primordial power spectrum from the CMB, where the CMB is measured at 0.05 h per megaparsec. This is measured at 0.78 h per megaparsec. So what this means is that you should look at these parameters in these chains and translate them mentally. So NP is going to be the same as NS in a model with no running. AP, however, is going to be much less than the AS you get from the CMB because it's measured at small scales and the power spectrum is a little bit rare. We also include the Hubble parameter. We include this for technical reasons. It helps deal with cosmic variance, but it is actually not really measured by the Lyman-α Forest. There's really no sensitivity to it in the Lyman-α Forest at all. We also show the growth rate, omega matter h squared, and that's really just there because we marginalize over the small uncertainty in the forest, but it's much better measured by Planck. And we include several parameters for hydrogen and helium ionization. So here is the full list of the parameters we're looking at together with their ranges. The crosses show the location of the parameters we ran low fidelity simulations at, and the circles show the locations of the parameters we ran high fidelity simulations at. And you can see they span the parameter space pretty well. These 3 parameters, ZI-HE is the beginning of helium reionization, ZF-HE2 is the end of helium reionization, and this alpha Q controls how hot the gas gets during helium reionization. This ZHI is the redshift of the midpoint of hydrogen reionization. So I've been talking about hydrogen reionization, so just quickly, let me explain what I mean here. So uniquely amongst these simulations, our boxes are very large, and that means that they're large enough that we can resolve the bubbles on which reionization happens, and so we can include the effects of patchy reionization on the Lyman-α Forest. So we have a patchy hydrogen reionization model, so we include all the effects of hydrogen ionization at lower redshift. We also have a patchy helium ionization model. This involves the placing of 30 megaparsec ionizing bubbles, which heat the gas within their bubble and cause the overall ionization fraction to change from 0 around redshift 3.8 to around 1 at redshift 2.8. And the effect of this is to heat the gas to match the observed IgM temperature, shown by this black line with gray bands around it. So here I've shown the best fit IgM temperature from several of our simulations, and you can see that the ones that are fitting to the observed data points, which are this gold and blue line, that's what the plus T0 means, they're fitting to this data set, they do in fact match it. So we are able with our model to marginalize over the parameters of helium ionization and produce a pretty reasonable match to the observed temperature of the IgM. Now I've demonstrated that we can match the observed IgM temperature. I want to demonstrate that our likelihood function that our chains are actually working. So I'm going to show you here the posterior constraints from a simulated data set. So I took one of the high resolution simulations in our training set. I generated a flux power spectrum from it. I threw it through the likelihood function, produced Markov chain Monte Carlo chains, and you can see that the known parameters of the simulation are shown by the dashed red lines, and the 1D posterior parameter constraints are shown by these black circles. And you can see that we do indeed, the dashed red lines lie roughly within the middle of these black circles. So we do indeed recover the input parameters pretty well. This likelihood function is able to marginalize over nuisance parameters connected with all the things that you think a Lyman-α Forest likelihood function should have. This includes metals, damped Lyman-α systems, and of course we have an extra likelihood function for the temperature data. So what we're going to do here is we're going to compare to the eBOSS SDSS DR14 release. If you look at the previous papers on this, you'll see that there's a mild tension with Planck. This is because eBOSS prefers NS a little bit lower than Planck by about 2 sigma. One of the things you're interested in is, why is this the case? It's not a large tension, but it would be nice to understand. Here are our results. These are preliminary results from taking our model and our likelihood function and comparing them to SDSS DR14. One thing you can notice, and we've done one thing here. So this blue line is a comparison to all the data available to us. So both the temperature data and the flux power spectrum data from redshift 2.2 to 4.6 from eBOSS. And this is the blue line here. And you can see that the tension that we have with Planck has now gotten much worse. Now we have NS of about 0.9 plus or minus a wider margin. This is unfortunate. This is much too low compared to Planck. We also have a P a little bit low compared to Planck, which is also a little strange. Notice that the helium ionization parameters are really being measured by the temperature data, and they're not being measured very well by the flux power spectrum data at all. Right? So the mean IgM temperature is constraining how helium ionization behaves and how hydrogen ionization behaves. So when we first got these results, we were puzzled, but then we investigated further, Martin investigated further, and we discovered that this is really driven by the lowest redshift bin, by redshift 2.2 and redshift 2.4. And that's the thing that drives the low NS. When we run a chain excluding these things, we get an NS which is much closer to 1, and which still includes the range allowed by Planck. So what's going on here? So what we did was we pulled out our best fit flux power spectrum and we visually compared them to the model. And so here in the red, I have the reduced redshift range between 2.6 and 4.6, and in the blue, I have the full redshift range. And you can see that these are both reasonable matches to the high redshift data. But when you look at the redshift 2.2 data set and the redshift 2.4 data set, yeah, the blue line is kind of closer to the data, but it's still pretty discrepant with it. And the red line is a long way off. So it's really these lowest redshift bins that are driving the discrepancy. And the reason they're driving the discrepancy is because they are inherently inconsistent with our best fit model. So even the best fit model using all the data set is still not in great agreement with this low redshift data. The chi-squared is too high. So why might this be? So there are two possibilities. One possibility is that there is an incomplete theory model, that there should be more parameters in the theory model, that there should be more cosmological parameters, for example. I don't think this is a cosmological effect because most cosmological effects do not suddenly appear at redshift 2.2. One possibility is that there is in the real universe a much stronger AGM feedback model than we use in our simulations. This would have to be a much stronger AGM feedback model than is included in modern day cosmological simulations. It's completely possible but I think it's unlikely. You know, we build our feedback models to match observations in the real universe. So you'd have to get a bit creative. Nevertheless, it's a possibility. Another possibility is that this is a systematic in the lowest redshift bin of the eBOSS Lyman-α data, which again is possible. I mean, this is the bluest redshift bin, so it's possible that something's going on. So to try and figure out what's going on, we compared this bin at redshift 2.2 to other data sets, including the newly released DESI early data release flux power spectrum at redshift 2.2. And you can see that there isn't actually a lot of agreement between the various Lyman-α flux power spectra of this redshift. A higher redshift, the agreement is much better, but a lower redshift, they're a little bit discrepant at a couple sigma level. And this is not conclusive that there is a systematic in eBOSS. I want to emphasize that. The error bars of the other data sets are a little bit larger than eBOSS. And in addition, it could very easily be that, you know, DESI, the new instrument, that there's a systematic in the other data sets, and that eBOSS at the 1 to 2 sigma level, and that eBOSS is completely correct. And this is a theory issue. However, it is suggestive that the fact that these data sets do not really agree is suggestive that there's something still to be understood here. Let me just go back to my parameter chains and say the parameters the chains that I like the most are the ones between redshift 2.6 to 4.6, excluding the 2 lowest redshift bins, just in case it's a systematic. I want to take these numbers and compare them to the Planck values. So NS here is best fit by 1, but it is consistent with the Planck value of 0.97. There's a fairly wide range here. If you take the constraints on the amplitude of the power spectrum, that's the AP parameter, and translate it into sigma rate, you get a sigma rate of about 0.8, plus or minus some reasonably large error bars. So these are in reasonable agreement with Planck, and we will in future run joint chains using both the Planck likelihood and the Lyman-α likelihood, and test exactly how consistent they are and what the preferred cosmological parameters are. So just to conclude, we've completed a reanalysis of the eBOSS Lyman-α data. We've used the PRIA Cosmology suite and multi-fidelity emulation to build a wonderful interpolating emulator for the Lyman-α Forest and to plug it into a likelihood function. Generally, because we're excluding the lowest 2 redshift bins, which have the best statistical error, our constraints are generally a little bit weaker than those that preceded us for previous analyses. I would like you to interpret this as a positive thing, consider it more room for theorists to make theories and more employment for theorists. And this will really remain the case until the DESI year 1 flux power spectrum. So that will be the first data set that has smaller error bars and is able to make the constraints tighter again. So thank you very much for listening. I leave you with the archive.